Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU, Bhilai. In this tutorial, we discuss about the Floyd-Warshalls algorithm. This is under the graph theory. And this algorithm basically used to find out the shortest path between the vertices, or we can say stations. So first, to understand the introduction part, what is this algorithm? What is a Warshalls algorithm says? So the Floyd-Warshalls algorithm is an algorithm that computes the shortest paths in a graph with positive or negative edge weights, but with no negative cycles. So it is considered both positive signs also and negative weights also, but the main focus in that with no negative cycles. You have to concentrate. If there is cycle will be created, you have to remove that cycles. So a single execution of the algorithm will find the length. It means some weights of the shortest path between all vertices, all pair of vertices, through it does not return details of the path themselves. So in this algorithm, we focus on different topics, like first we understand why we require this algorithm, what is this algorithm. Next, with the help of any one example, we can understand how to find the shortest path between the vertices or the stations in this algorithm. Next, application of this algorithm, advantages of this algorithm, and also we discuss about the disadvantages of this algorithm. So one by one we can understand the overall principle or overall property of this Warshalls algorithm. So first we go for the what is the Warshalls algorithm. So the Floyd-Warshalls algorithm is a graph analysis algorithm that can be used to find the shortest paths between all pair of nodes in a graphs. It is named after Robert Floyd, who published this algorithm in 1962. The algorithm works by iteratively updating a matrix of shortest path weights until the matrix coverage to a final state. So the matrix is initialized such that the shortest path between any two nodes, or we can say vertices, or we can say stations, is infinity or some large values, then the algorithm relaxes all edges in the graph one at a time. One by one we can consider one vertices, then we free the maximum weight edges by the replacement of the smallest weight edges. We can see in the examples how we perform this theory to implementing the practical approach. So for each edge, the algorithm updates the shortest path weight for the start and end nodes of the edge. If the new path weight is lower than the current shortest path weight. After all, the edges have been relaxed. The shortest paths between all pair of nodes will have been found. So, the Floyd-Warshalls algorithm can be used to solve many different types of problems, including finding shortest path between two nodes in a graph, finding the length of the shortest cycle in a graph, and detecting whether or not there are negative weight cycle in a graph. So basically a three principle where the shortest path algorithm is focusing. We can see by an example one by one. So move on the algorithm part. So when we working on the Warshalls algorithm, we require some graph, like when we moving, suppose we want to travel a Delhi to Mumbai, we having a lot of approachable path to reach the Mumbai station via Delhi, and you going by a road connectivity, you having a multiple option to reach over there. So which path, which edges we have to select to reach the destination stations. So having an optimum path, you have to focus on a lot of factors like a distance, like a traffic, like a conjunctions. So a lot of factors you are focusing. Based on that one, you are selecting a good path to reach your destination in a minimum time. So for this one, we can go for the Warshalls algorithm. Why? For this one, we require a Warshalls algorithm. So consider a graph. Suppose G is representing a graph, and G is the combination of two important factors. One is a V. V is represent for vertices, and E is a represent of edges. So where V is the set of all vertices present in the graph, and capital E is the set of all the edges in the graph. The graph G is represented in the form of an adjacency matrix. We can understand this adjacency matrix, how we create adjacency matrix. A that contains all the weights of every edge containing two vertices. So we can understand the algorithm step by step. In a step 1, construct an adjacency matrix. We can call the name as any alphabet or any letter via variable. Here we take a with all the cost of edges present in the graph. If there is no path between two vertices, it means we are talking about the direct path. There is no any edges between the two vertices, then mark the value as infinite. In the initial stage, we can't reach from source station to destination station directly, but in a future we can reach by the help of another station. So it should be replaced by the maximum value. So initially we have, when we having no direct path or no direct edges between the two vertices, or we can say two station, at that time we put the value as a positive infinite value. Obviously, when we having a path in a future, the cost of this one, or we can say the weight of that path, is really is the minimum of as compared to this positive infinite value. So in a future, we can replace this infinite value by the small weight value. So initially, when we don't having a direct edge or any path between the two vertices, initially we put or mark the value as infinite. Now step number 2, derive another adjacency matrix A1 from A. Initially A is representing a direct edges. Now we are considering a A1 from A, keeping the first row and first column of the original adjacency matrix intact in A1. And for the remaining value says A of ij, it means when I is a station, j is another station. When you're reaching from I to j with the help of A1 in A1 matrix, if A of ij is greater than A of ik plus A of kj, then here I or k means I is a source station, j is a destination station. With the help of k means with the help of another vertices, this is not a destination station, but suppose we having a, b and c, and we want to travel a to c. There is no any direct path between a to c, but you can move from a to b, then b to c. By this vertices you can reach your destination. Obviously this is I, this is a j, and this is a k. With the help of I, you can travel I to k, then k to j. So with the help of that another vertices, you can move or you can reach your destination station. That's why we using a 3 alphabets, three characters I, k and j. So initially we want to travel from a to j, I to j, but with the help of k. That's why we taking this syntax: a of I j is greater than a of I k plus a of kj. I k then plus k of j. Then replace a of ij with the a of ik plus a of kj. Otherwise, do not change the value. Here in this step, k equal to 1, first vertices acting as a pivot point. So we consider the first vertices as in the picture, and it will help in a particular graph to, by the access of this station of with this vertices, you can move any station with the help of that. But remaining all the vertices are considering as a graph, but they can't help you. Only a first vertices in a first step, it will give you facility to take on access on that path, that's the station, and you can travel to any station if you are having a direct path. Now in step number 3, repeat step 2 for all the vertices in the graph by changing the k values for every pivot vertex until the final matrix is achieved. Suppose it's completely depend on the how many station you cover inside the graph. Suppose you considering a 5 station in your graph, so it means one by one you can fetch all the vertices like first was the A1, then A2, then A3, then A4, then A5, like that. Suppose you are having a station A to E, and that one first you consider A, then B, then C, then D, then E. One by one all the station will be covered, and all the station will give you access to take a facility from this own station to reach or another station. So we can't take all the station at a one time, but we take single station at a one time, and one by one it will consider all the station. What we consider in the first step, it give you facility, and then we take move on the another station also. Suppose first we take a A1, then we take a B station, or we can say A2. Then when we considering a A2, A1 is also here, also in the picture also. Then after then A3, so A1, A2, then A3, all 3 vertices are come in the picture, and all the 3 vertices give you facility to reach your any station. Process is going on until all the vertices we don't cover. So until the final matrix is not achieved. So in a third step, we focus on all the vertices one by one. Now in step number 4, the final adjacency matrix obtained is the final solution with all the shortest path. So in the final answer, we can get all the positive values to reach one place to another place in the particular graph. Now, whatever talking about the theory, we can understand by the example. So if we can start with this example. Now here we are having an example like consider the following directed weighted graph. Now you already understand the concept of the directed, weighted. Already we covered this weighted, directed, undirected graph in the previous tutorial, like a graph in a graph theory. So by that particular concept of we applied here also. There is a directed weighted means we are having a 2 station, we are having a directed edge between two stations, and that particular edge having a direction also. Suppose A to B having a edge and also having a direction. If we don't having a direction, so you can travel in both way, A to B also and B to A also. But if you having a direction, it means when you A to B and arrow should put it on towards to B sides, then you move only from A to B, you can't move from B to A. So this is a concept of direction. When direction is given in the graph, so you can focus on the direction for traveling towards that particular direction. You can't bidirectionally movement. But when the graph is undirected, you can move both directions at the same time. So consider by the same weight also. So consider the following directed weighted graph. It means on the edge we having put some weight on that particular edge. It means it's a combination how much time it will take, the conjunction, and lot of factor will be considered inside the weight. If weight is high, then definitely it will take up more time, more complexity to reach the destination. So in a following directed weighted graph, G is representing VE for the shortest path between all the vertices of the graphs using the Floyd Warshalls algorithms. So now start down. Step number 1, construct an adjacency matrix A with all the distance as value. So focus on the graph and draw the adjacency matrix. Then step number 2, considering all the above adjacency matrix as the input, derive another matrix in a first form, that is A0. In A0, we replace all the values which are don't having direct edges by the infinite value. By keeping only one rows and column intact, take k equal to 1 and replace all the other values like by the a of ik plus a of kj. That is depend on the if a of ik and a of kj is less than the as compared to a of ij, then we replace the new value. In step number 3, considering the above adjacency matrix as the input, derive another matrix A0 by keeping only first row and column intact. Take k equal to 1 and replace all the other values by the same formula a of ik plus a of kj. In step number 4, considering the above adjacency matrix as the input, derive another matrix A0 by keeping the first row and the column intact k equal to 1 and replace all the other values by the same formula a of ik and a of kj. In step number 5 and step number 6, we take all the values one by one and finally we reach to our final matrix by the whatever the vertices will be given in the graph. Now, to take a simple example, here we having a 4 vertices. So, either in a question in a university papers, either we give you a matrix, either we give you a graph. So, most of the time you having a graph and based on that graph, you have to draw the matrix. So, here we having a graph like first we focus on how many vertices in this graph. There we having a 4 vertices like in the form of R, S, T and U. So, we having edges also. So, one by one we draw the adjacency matrix by this weighted graph. So, how we create an adjacency matrix? Take a one symbol that is called a W and W is representing for the weight. Now, weight equal to, now draw the matrix. So, in a row and a column, this is a 2D graph and a 2D matrix. So, how we create that? So, now we take all the vertices in a column wise also and the row wise also, like R, S, T, U, we can write in a vertical form also, and also you write R, S, T, U in a horizontally also. One by one you can match. So, first one is a R2 R. The first column, first row, first column value is. So, first column and first row value is R2 R. You can see, go to the graph and check, can we having a self loop from R2 R? Yes, we having a self loop R2 R and the weight of that particular edge is that is called as 7. So, we put the value 7 where at the position R2 R, or we can say the first position and the first column of that one, the value is R2 R this 7. Now, we cross check another direct edge from R to S. Now, the row is same. Now, we focus on the next column. So, row is the first row. Now, we put all the values in a row wise. So, first we take a R to S. Can we having a direct edge from R to S? Yes, we having a direct edge R to S. That's the weight is 5. That's why we pick that value 5 and put where from R to S the first row second column. The value is 5 because the 5 is take from the direct edge from R to S. Now, we focus on the third column, or we can say first row third column, the value R to T. Can we having a direct edge from R to T? No, we do not have any direct edge from R to T. So, we can't put any values. If we insert here, we has a 0 value from R to T. Now, we go for the R to U, last first row, last column. Can we have a directed? Here we having an edge from U to R. This is a directed graph. That's why I'm telling you the direction is so important. We having an edge between R to U, but that the edge is a directed graph and the direction towards the R vertices, not to U vertices. That's why we can't pick the value 4 and insert over there. Here we don't have directed edge from R to S. So, we pick the value as a no value, that is called a 0 value. Now, by this you understand how we pick the values and how we write the values inside the adjacency matrix. Again, we understand the second row and the first column. So, second row is basically starting from the S. So, S to R. So, for second row, first column, again we start S to R. Can we having a direct edge from S to R? Yes, we having a direct edge. S to R, the value is 7. So, pick the value and put over there in the matrix. Can we having a direct edge from S to S? There is no any self loop from S to S. So, we can't put any value. So, over there we put the value as 0. Now, again can we having a direct edge from S to T? We having a edge, but that is there's a directed edge, and the edge is towards the S vertices, not to T vertices. That's why we can't take the value 3. Here we having a no direct edge from S to T. That's why I put the value as 0. Now talking about the S to U. Can we having a direct edge? Yes, we having a direct edge, and that is a towards the U directions vertices. That's why we take the value, and the weight of that particular edge is 2. That's why we pick the value and put over there in the form of 2. Now we go on another vertices. The all row and all columns are already filled. Now we move on the third one. Third one is a T. Again we cross check. T to R. Can we have direct edge? No. That's why I put the value 0. Can we have a direct edge from T to S? Yes, we having a direct edge. That's why A weight is 3. That's why I put the value 3 over there in our matrix. Now we take another the T to T. Can we having a direct self loop? T to T? No, we don't have any self loop. That will put the value 0. Then next one is T to U. Can we have? No, no direct edge. There is edge between T and U, but there's a towards direction of T, not to U. That's why we can't insert a value. That's why we put the value 0. So all three rows are packed, and as well as column. Now move on the last vertices, that is called a U. So U to R, can we have? Yes, we have. That's our value is 4. Put the value 4. Now can we have a direct edge from U to S? No, we can't have. That's why we put the value 0. Now again we cross check S U to T. Can we have? Yes, we having a value, and weight is 1 also. That's why we put the value 1. Can we have U to U, or we can say self loop? No, there is no any self loop from U to U, so we pick the value, put the value 0. By this, all the rows and all the columns. If we having a 5 vertices, so we can draw or more columns, but here we having a 4 vertices only. That's why we take this matrix, adjacency matrix is 4 by 4. If we having a 5 vertices, so at that time we cross a 5 by 5. We having a 7 vertices, so we cross the 7 by 7. That's completely depend on how many vertices in a graph that is reflect to the adjacency matrix. Here we having a 4 vertices. That's why the adjacency matrix is 4 plus 4. And by this you can understand how we put the values inside the adjacency matrix. Now we start the operation part. Now it's the first one, that is a A0. Either we can take any variable, that is a Q0 also. So first we take a Q0, and a Q0, what you do? You replace all the 0 value by the infinite value, because there is no direct edge between any 2 vertices, but in a future you having a path from another vertices to reach over your destination. So you can, that time you can replace the old value by the new value. If the new value is lesser than the old value, you can replace it by the old value. So you can, in the first step, you can replace all the no edges between the vertices by the infinite value. So we take a same vertices, same matrix, the last matrix, and we replace like 7, 5, and third value is 0. Here we replace 0 by infinite, fourth value again by 0 by infinite, and based on that one, where we having a 0 values, we replace all these 0 values by the infinite value. But all the values where we having a 7, 5, 7, 2, as it is, there is no changes in that particular side. And particularly when you drawing a adjacency matrix, you also draw the path matrix also. So you can see here we having a path matrix in the currently right side of the adjacency matrix. There's a path matrix. The first one, the name where we putting the value 7, it is representing the particular vertices, that is called R to R. 5, it means R to S. Third is infinite, it means here we insert a dash dash. Third one, second row, first column is S to R, because we having a direct edge. So here we having 7 value, that's based on the S to R, and dash dash, then finally last value is 2, that is a S to U. Then third one is again infinite, it means dash, and next is a T to S, that's why take a 3 having a value, that's based on the T to S, that we take a TS, and all are dash dash. And last one is last column, first row is a 4, that is completely come from the U to R, that's why we take a UR, then again dash, and 1 is a U to T, it means UT, and the finally is a dash. Basically, this path matrix you can understand by the path matrix from which station you can pick, via which station you can travel, and which destination you are ending when you reach your destination. So by this example you can understand easily from where you changing or from which path you can taking to reach your destination. So this is a Q0 matrix. By the Q0 matrix, again we cross check the Q1 matrix. Now Q1, as I told you in the algorithm, you can take one vertices as a complete, give you complete facility to access that station and reach any station also. So first you take that same thing, R to R. So R to R, can you moving another way to reach your destination R to R? No, there is no any destination. That's why we take a no any direct edge. So we take a old value. We can't replace the new value because there is no any R to R to give you permission. So there is no any value. There is a 0. That's why we take old value is 7. That's why we take a R to R. There is a 7 value. Now again second one is 5. Yes, again is 5. No changes. There is no any path from R to S. So that is taking a 5 also. Now again third one is infinite. Fourth one is infinite. No direct. R will not help you directly or indirectly to reach the other station. Now move on the next one. That is a second row, first column. So again second row, first column is 7. First one is a S to R. So you're having a direct edge S to R. So that's why you take a value as S to R. Now next one. Next one is a S to S. So have you cross check S to S in a Q0 adjacency matrix? There is a no direct edge between S to S because there is a no any self loop on S to S. But when first vertices R give you permission, you can access the R. Can we travel S to S? Definitely we can travel from S to S. Why? We are having a one path. First we travel S to R, then R to S. We can travel. We can reach your destination S to S. There is no any self loop, but access another vertices give you permission to take the facility from that vertices and reach to destination. So S is a source station, S is a destination station. There is no any self loop, but with the help of R you can move from S to S with the help of R. The total cost is initially cost is infinite, but the new cost is S to R is 7 and S to S is 5. That we take a value that's a S 7 plus 5, that is a 12, and 12 is less than the infinite value. That's why we can write 12 or replace the infinite value by the 12. Now also we write the adjacency path matrix where we having a dash in the previous one. Right now we write down S R S, S to R, R to S. By this traveling we can write the new value 12. Now third one, no any changes because no any with the help of R we can't access that particular station. Now finally last one is S to U. That is no again no any direct. Already we having a 2 the minimum cost with no any new edges to buy the travel with the help of R replace this old value. Now move on the third one. Again third row, again we can't first position T to R, there is no any direct edge, that's why dash infinite value. Again T to S, same 3, then T to T, T to U, again dash dash, no any changes. Now next one, last one, U to R. We having that U to R, already we having old value that is called a 4. Now second one is U to S. Now again cross check. There is no any direct edge between U to S. You can't. S to U having a path, but U to S we don't move anywhere. But with the help of R, can we move? Yes, we can check. U to R and R to S we having edges, 2 edges. With the help of this 2 edges, U to R and R to S, the total cost is, again we calculate, the total cost is a 9. So 4 plus 5 equal to 9. And the 9 is lesser than the previous old matrix value that is called a infinite. So we can replace this value by this new value that is a 9. So we can mark 9, and also we put this circle also. For this we understand which value we will change in this matrix. Now next one is UT, that is already 1, and the final is infinite value, that is called a dash. So you understand, here we change two values. First one is a S2S and second one is a U2S. Here we change two values in this matrix. Rest, where is no need changes, all the values are remaining are the same, only the two changes here we done. We can mark by the circle. Also we write down the in the path matrix like a SRS and URS. Now move on to another one, that is a Q2. Now R give you facility. Now another vertex also come in the ready state. It will give you facility to access his property also. So R as well as the S, both vertices give you facility to take his property and to reach your any station. So both are in the ready state. R is already ready state and S is also a ready state. Now again we cross check. So first one R2, R7 same, it is R2S again same 5. Now third value is R2 T, no any value, that's why infinite value. Then R2U, can we move to R2U? Yes, we having R2U, initially the infinite value, but R2U we having a path, with the help of S we can move R2S and S2U. So the total cost is a 7 and 7 is less than the infinite value, so we can replace this 7 by this value. So first changes will be come out, the 7 will be marked as a circle, and that is in a path matrix you can write RSU. Now second row, 7 as it is no changes, 12 as it is no changes, already we done. Third one, there is a no direct edge from S to T, again infinite. Then S to U again 2, there is no any changes, no any minimum cost will be available over there. So we can replace this particular matrix. Now again we check T to R. Now here we check here T to R we having a edge, but that after we calculate the T with the help of S, T to S and S to R, the total cost is 10 and the old value is 12. So 10 is less than 12, so we can replace that one. Yes, definitely we can replace that one. T to S and S to R is the minimum cost as compared to the previous value. So here we replace the new value by the old value. So here we put the 10. Now TSR we having a initially we know any value. There is a infinite value, or the infinite value will be replaced by the TSR. So with the first two travel T to S and S to R, the total cost is 10. So you can replace this new value by the old value, that is all 10. Now again next value is T to S, there is a 3, no changes. T to T, there is no any path or any edge, direct edge, or no any path with the help of R or S. So again we put the infinite value, and the last one is now we having a R T to U, there is no direct edge, but with the help of S you can reach your destination, that is called a U. So T to U, first you travel T to S, then S to U. The total cost of T to S and S to U is 5, which is less than the previous value. There is a infinite value. Here we can replace the new value by with the help of 5. Now again the last row where you are having a U to R, again same value 4. URS, now again you replace this value by the 9. So U to R and R to S, you can reach your destination. So again 9 is less than the previous value, you can replace this new value by the old value. Now U to 2 again 1, and U to S. Now U to S we are having a path U to S to travel U to R, then R to S. So here we are having a value is 11. So you can write URS in the path matrix and also put the values 11 over there. So here we are having a few changes, and again we are having a 3 remaining values. There is an infinite value. Then we check another matrix, that is a Q3 matrix. Now come on the Q3 matrix. So again we cross check in the first row, first column like that, R2R no changes, R2S no changes. Third one R2T no changes, again infinite value. R2U, yes we are having a changes, R2S and S2U. Now we are having a value is a 7. So 7 is updating, and now we change the 7 value. Now again in a second row, again you cross check S to R, SRS, again same thing. S to T, there is no any direct edge, that again we put the infinite value. S to U, again you having a 2 value, again no changes. And the third one TSR, again the same thing with the help of TSR, again we having a 10 value, you can't find out the new value. Now again T2S, again you having a 3 value, can't find out the new values. Again next one is a T to T, there is no any access in a with the help of T also. Now we having a 3 vertices T, S and R. All the vertices give you permission to reach your destination T, S, R. So again in infinite value. T, S, U is a 5 value. Now again change U to R in the fourth column. U to R is a 4. U, T, S. Here we can replace U, T, S with the help of T. You having reached to destination S with the help from U. U, T, S is a 4. So 4 is replaced the old value. That is 4 is a less value as compared to the old value. You can replace the 4. Now U to U 1 and U, T, again one more changes. U to U. You now again you having a new path. U to T, T to S and S to U. This is a value is 6, which is lesser than the old value. You can replace this value by the old value. So the final matrix of this one. Again we having a 3 infinite value. Now again we check the another matrix. Now we consider the U matrix also come on the picture, and U is also coming on the ready state. Now we take a last matrix, that is a Q4. Now all the vertices come on the ready state, come on the picture. Now one by one click on check. R2R same, R2S is same, R2T. Now we have to change this value. R2S, S to U, U to T. We having a path. This path total cost is 8, which is less than the previous value, that is called a 8. And RSU again 7. Then again change S to R 7. S to S. Now again we having a new path. S to U, U to R, R to S. This is a total cost is 11. This is a minimum of previous value, that again we replace that one. S to T, again we replace that S to U, U to T. The new value is 3. 3 is lesser than the previous infinite value, that we can replace this new value. S to U, again 2. Next one is T to R. Again you having a new part. T to S, S to U, U to R. This value is 9. This is lesser than the previous value. You can replace these new values. T to S also is a 3. T to T. Yes, you having a new path. T to S, S to U, U to T. This new value is 6, and 6 is replaced by the previous value. So next value is T to U. Again you can replace T to S and S to E. That is the new value is 5, and 5 is lesser than the previous value. Lot of value are changes in this particular matrix. Then U to R again 4. U to S now again is 4. U to T is 1. But U to U, you have a new path. U to T, T to S and S to U, and the new value is 6, and 6 is lesser than the old value. That's why we can say that this complete matrix, this is the shortest path matrix to traveling from any source station to any destination station. This is a particular cost from one station to the another station. And also we write all the path matrix at the right side of the particular matrix. So by this formula you can calculate the minimum value, like you have to travel Q4 to 2. 4 is a one vertices, 2 is another vertices. So take a minimum of 4 to 2 old value, and take a new value like a 4 to 1 and 1 to 2. If the new value, the old value is infinite and new value is 4 plus 5, that is a 9, and 9 is less than the infinite value, you can change the new value because it is lesser than the old values. So by this logics you can replace the new value by the old value. So analysis for the pseudocode above, the Floyd Warshalls algorithm operates using the 3 or the loops to find the shortest distance between all the pair of vertices within a graph. Therefore, the time complexity of the Warshalls algorithm is O of n to the power 3, where n is the number of vertices in the graph, and the space complexity of this algorithm is O of n square. So time complexity is O of n cube, and is a space complexity is a O of n square. So by this algorithm, first you calculate, you take a Warshalls algorithm, you take a loop I from I1 to n, then j from 1 to n, k from also 1 to n, then repeat from k1 to n to do compute d k from d k minus 1. If d of I k plus d of k j is less than d of I j, so you can replace d of I j with the help of d of I k plus d of k j. Return to d equal to 1 to n. So finally, the applications of Warshalls. There are many applications of Warshalls algorithm. Some of the most popular applications are finding the shortest path between the two vertices in a graph, detecting negative cycles in a graph, and computing the transitive closure of a graph also. Well, Warshalls algorithm can also be used for other purpose, such as solving the all pairs of shortest path algorithm in weighted graph, finding the closest pairs of vertices in a graph, and computing the diameter of a graph also. So directed graph, to find the transitive closure of directed graph, to find the inversion of a real matrix, for testing whether an undirected graph is bipartite. So finally, advantages. So Warshalls algorithms is an incredibly powerful tool that can be used to solve a variety of problems. In the article, we will take a look at some of the advantages and using the Warshalls algorithm. One of the biggest advantages of this Warshall algorithm is the versatility. The algorithm can be used to solve a wide range of problems, including finding the shortest path between two nodes in a graph, calculating the transitive closure of a graph, and detecting negative cycles in a graph. Another advantages of this is simplicity. Unlike some other algorithm, this Warshalls algorithm is relatively easy to understand and implement. This makes it an ideal choice for a student and professional who are just starting out with graphs algorithm. This algorithm is very efficient. It has a time complexity of O of n cube, which means it can handle large graph with ease. Additionally, the algorithm is parallel, meaning it can be run on multiple processors to further improve its efficiency. There are few disadvantages also. They are using this Warshalls algorithm. It is quite complex and can be difficult to understand, can be slow when used on large graph. So does not always find the shortest path between two nodes. It can sometimes find a path that is longer than the shortest path. So finally, I hope you understand the concept of today's Warshalls algorithm. So thank you.